When we're finding limits, it's pretty common for us to encounter 0 over 0 as we take a limit. For example, here we have 1/2 to the x minus 1 all over x, and x is getting closer and closer to 0. So we can see what's going to happen here as x gets closer and closer to 0. 1/2 to numbers closer and closer to 0 will be closer and closer to 1. So we'll have 1 minus 1 over 0, but of course 1 minus 1 is 0. So both the numerator and the denominator are approaching 0 as x tends to 0. And sometimes what we've been able to do is to simplify, but sometimes in a case like this it's not exactly clear how you would simplify. What could you do? But we can come up with another technique if we're just a little bit crafty here. So the general case is that you have x approaching some value, let's call it a, and you've got a numerator function and a denominator function. And as x gets closer and closer to a, both of those functions are going to 0. Let's assume that the functions are nice enough that they both have a first derivative at that point a that x is approaching. Then we can pull a little trick in that case. First thing I'm going to do is write this limit as f of x minus f of a all over g of x minus g of a. Now the reason I can do that is because f of a and g of a are both 0. So when I write f of x minus f of a, then I'm really just subtracting 0, so it's the same thing. What I'm trying to do is to weasel a little derivative in here. So I have so far the change in f over the change in g. For each of those I need to divide by the change in x. So if you go from a to x, then the distance that you've gone in the inputs, or the change in the inputs, would be x minus a. And I see that I can divide top and bottom by that quantity x minus a. Oops, this is the limit as x tends to a. And now I can apply the property that if they exist, the limit of the quotient is the quotient of the limit. So we have the limit as x tends to a of f of x minus f of a all over x minus a divided by the limit of the denominator function, which is g of x minus g of a all over x minus a. And this function in the top, this limit in the top, is actually the definition of the derivative, right? We have the change in f over the change in x, and we're making those changes infinitesimally small. So this is f prime at a here, and down below this is the definition of the derivative of g at a. This is g prime of a. So we can see that if the functions in the numerator and the denominator are both going to 0 and they both have a derivative at that value a that we're approaching, then you could trade this limit in. The value of the limit is just going to be f prime at a divided by g prime at a. Let's see how that applies in this case. We already got 0 over 0. We can see that the numerator function is 1/2 to the x minus 1, and it's going to 0 when you plug in 0. And the denominator function, in this case, that function is x. So we calculate the derivative of the numerator. When you have a constant to a variable, that's an exponential function. The derivative is going to be 1/2 to the x times the natural log of 1/2. Down below, see, the derivative of g is 1, because the derivative of x with respect to x is 1. The value of a, in this case, is 0, because x is approaching a. So f prime at 0 is 1/2 to the 0, that's 1, times the natural log of 1/2. And g prime at 0, and g prime is always 1, so g prime at 0 has to be 1. So what this rule tells me, it's called L'Hopital's rule, it says that that limit that was 0 over 0 is actually the natural log of 1/2 over 1, which is the natural log of 1/2, or if you like, since 1/2 is 2 to the negative 1, I could use the property of logs that lets exponents come down in front. So we have the negative natural log of 2 as the limit there. Let's do another example. In this case, we have x tending to 0. The top is getting closer and closer to 0, and so is the bottom. The function in the numerator is 2x plus 4x squared minus 7x cubed, and the function in the denominator is 5x plus 3x squared plus 11x cubed. We can see that both are going to 0 as x approaches 0. So we try to apply L'Hopital's. We find the derivative of the top and of the bottom. The derivative of the top would be 2 plus 8x minus 21x squared. the derivative of the bottom, g prime, would be 5 plus 6x plus 33x squared. So the value of the derivative at the point we're approaching, which is 0, for the top is 2, and f prime at 0 is 2, and g prime at 0 is 5. Then by L'Hopital's rule, since we had this 0 over 0, we know that the limit is going to be actually 2 over 5. Sometimes L'Hopital's rule needs to be applied a second time. So here's an example. We have x sine x over 1 minus cosine x. So our top function, f of x, is x sine x. So its derivative is the derivative of the first, which is 1, times the second, which is sine, plus the first, which is x, times the derivative of the second, which is cosine. The bottom function, the denominator function, is 1 minus cosine x. Of course, the derivative of 1 is 0, and the derivative of the negative cosine is the positive sine. But here's the problem. We're approaching 0, and f prime at 0 is the sine of 0 plus 0 times the cosine of 0. That's going to be 0. And g prime at 0 is also 0. So we try to trade this in for f prime of 0 over g prime of 0, and it doesn't work. We need something a little bit stronger. And it turns out you can prove a slightly stronger form of L'Hopital's rule if you use Cauchy's mean value theorem. So here's what it says. Instead of having just the derivative of f at the point you're approaching over the derivative of g at the point you're approaching, you have the limit as the value goes to the point you're approaching of the derivatives. This is good, like in the case before, because now, since we have a limit that's turning out to be 0 and 0, we could apply L'Hopital's again if we wanted. So let's do this way, using this stronger form that lets you trade a limit in for a limit. So we're going to trade this in for the limit as x tends to 0 of the derivative of the top, and we figure out the derivative of the top was the derivative of the first times the second plus the first times the derivative of the second, all over the derivative of the bottom, which we found was sine x. This is by applying L'Hopital's rule, so I'll just write a little note here above my equal sign so everybody can follow what happened. Now again, I get 0 over 0. So looking at this, I know I have 0 over 0 as x tends to 0. And since this satisfies L'Hopital's rule, we've got two functions. They're differentiable, and it's approaching 0 over 0. Then I can use L'Hopital's rule again. So as long as I get 0 over 0, or it turns out infinity over infinity is okay as well. As long as I get 0 over 0 or infinity over infinity, I can apply L'Hopital's. The derivative of sine is cosine. The derivative of x cosine would be the derivative of the first, which is 1, times the second, so there's another cosine, plus the first, which is x, times the derivative of the second, which is negative sine. So we get minus x sine x all over, let's see, the derivative of the sine is the cosine. And now we can take the limit, because the cosine of a number near 0 will be close to 1. The cosine of a number near 0 will be close to 1. And if this is near 0, the x is going to 0, so is sine. That's going to be 0. And then downstairs we have cosine. So we have 1 plus 1 minus 0 upstairs. The top's getting closer and closer to 2. The bottom's getting closer and closer to 1. So the limit is 2 over 1, or 2. So it took us two applications of L'Hopital's rule. One here, when we saw we had 0 over 0 the first time. We applied L'Hopital's rule and saw we had 0 over 0 again. So we used L'Hopital's rule a second time. And that second time, we got a limit that we could figure out. We got 2 over 1, which was 2.